Okay, so thank you very much, and hello also from my side. So today I will talk about our paper GradTree, Learning Axis-Aligned Decision Trees with Gradient Descent. My name is Sascha Marton. I'm from the University of Mannheim, and this is joint work with Stefan Lüttke, Christian Bartelt, and Heiner Stuckenschmidt. So let's jump right in. So decision trees are commonly used for many machine learning tasks, and this is mainly due to their high interpretability. However, learning a decision tree is a difficult optimization problem as it is non-convex and non-differentiable. So this is why the prevailing approach still is a greedy procedure that minimizes the objective locally at each internal node. So the commonly used algorithms are CART and C4.5, which I think most of you know. And they still remain largely unchanged until the 1980s. However, there is one big problem with these greedy algorithms as they constrain the search space, and this potentially leads to suboptimal trees, which is also well known in decision tree literature. So, but here you can see an example of two decision trees that were trained on the echocardiogram dataset. The decision tree on the left is learned with the greedy procedure using CART, and the decision tree on the right is learned with our gradient-based method. So the greedy decision tree starts with splitting based on the wall motion score at the root node, which is the local optimal split, and then on the percardial effusion in the second level. However, from a global perspective, it is much more beneficial to start splitting on the percardial effusion at the root node and then conditioned on the percardial effusion on the wall motion score in the second level. As you can see it on the decision tree on the right, which also achieves a significantly higher performance. So the problem is that the wall motion score is still the locally optimal first split, which is why a decision tree with the greedy procedure will always start with this split, which means that the decision tree on the right is not contained in the search space of a greedy algorithm and therefore cannot be learned with the greedy algorithm. So our idea now is to learn decision trees with gradient descent by optimizing all tree parameters jointly, which overcomes these limitations. I just want to quickly note that we are learning decision trees for fixed depth and prune them afterwards. So just that you don't get confused. So now you might be wondering, I previously said that decision trees are non-differentiable, and now I'm talking about learning them with gradient descent. So that's essentially what the rest of the talk is about. So first of all, we need an arithmetic decision tree formulation. So usually a decision tree looks, as you can see it right here on the left, and essentially is a concatenation of rules as you see below. And we want to transform it in an arithmetic formulation that only uses multiplication and addition, as you can see it on the right. So we essentially just replace the comparison operator with the Heaviside step function, which is essentially defined as 1 if the input is above a certain threshold and 0 otherwise. So it's essentially the same as the comparison operator, but outputs 1 or 0. So if we now replace all internal nodes with these Heaviside step function, then we can define the decision tree by multiplying the results of each path. And if we take now the sum in the end of all paths, then this results in the prediction of the decision tree, which is essentially the same prediction of the decision tree that we see on the left. So now the Heaviside step function, of course, still is non-differentiable, so we did not solve the differentiability issue yet. We'll come to this in a second, but before that, we need one more thing, which we call a dense decision tree representation. So we propose a dense representation which relaxes the split indices and split thresholds to account for the fact that the feature indices are categorical instead of ordinal. So essentially, we are transforming a decision tree as it's shown on the left into our dense representation that is shown on the right. Therefore, we simply one-hot encode the split indices, which means in root node, we're looking at x0. So the 1 is at position 0 in the first vector at the root node of our dense representation. At this left node in the second level, we're looking at x2, which just means that the 1 is at position 2 and so on. And similarly, we also store the split thresholds in a vector where the position always is at the same position as the corresponding split index. So now we have a representation that is well suited to optimize with gradient descent, but still we need to find a differentiable alternative for the Heaviside step function. And therefore we use the sigmoid logistic function. So we simply calculate the difference between an input value and a split threshold, and then plug this into a sigmoid logistic function, which results in an output between 0 and 1, where 0 would mean we're taking the right path and 1 would mean we're taking the left path. In our dense representation, this looks like this. So we're essentially just calculating the dot product between these two vectors to get the value of the split threshold, and we are also calculating the dot product of the split index vector with an input sample to get a corresponding value from the input, and then again calculate the sigmoid, the difference of the sigmoid function. So now this results in a value between 0 and 1, and not in a value of 0 or 1, which would mean, for instance, if we calculate a sigmoid function and get a value of 0.3, then this would currently mean that we were taking the left path with a probability of 30% and the right path with a probability of 70%, which would be a so-called soft decision tree. In the soft decision tree, you would take multiple paths at once, but this is not as interpretable. So we want to maintain these hard decision trees, which is why we simply round the output of the sigmoid function to main the hard splits. And there's one more issue, because these are now the parameters of our model, and during the optimization, of course, the parameters change and look, for instance, like this. And if we would now calculate the dot product, we would consider multiple features within a single split, which would result in so-called oblique decision trees, where the decision boundaries are not parallel to the axis anymore, but oblique with respect to the axis, and we will consider multiple features within a single split. So this might work well if we would have just 3 features, as in this example, but now consider a data set with 10, 20, or even more features. Then we would consider 10, 20, or even more features within a single split, which is again not interpretable anymore. And we are using decision trees mainly because of their interpretability. So this is why we apply. No, this is why we apply a hardmax function to enforce one-hot encoded split index vector, which then ensures univariate and axis-aligned decision trees. So now you might have noticed that we've again used 2 non-differentiable operations. So we are rounding and we are using a hardmax function. Both are non-differentiable, but this time we have an easy solution for this because we apply the so-called straight-through operator for the backpropagation of the decision tree loss to deal with these non-differentiable operations. So this essentially means during the backward pass, when the gradients are calculated, we exclude these operations, and during the forward pass, we apply them as is. So this introduces a mismatch between the forward and the backward pass, and this can lead to problems. So therefore, we need to ensure that the gradients are pointing in the correct direction. And this is also why we introduced all these things like the dense decision tree representation and using a sigmoid function for splitting, because thereby we ensure that the gradients are pointing into the correct direction and our model converges during the training. So now we've seen how we can learn decision trees with gradient descent, but the question, of course, remains, does this actually work in practice? And the good news is, yes, it works in practice. So this is the table from our paper for binary classification tasks. You can see our method in the first column. You can see a gradient-based alternative, which has some major differences to our method, which I cannot go into detail now in the second column. And then we have some non-greedy alternatives, which are using a genetic algorithm and using so-called optimal decision trees. And then we have the greedy procedure using CARD as like the current state-of-the-art benchmark in the last column. And as you can see, our method achieves the best performance on most data sets, and we also significantly outperformed our gradient-based counterpart. Also, there are some substantial performance increases on several data sets, as for instance, in the echocardiogram data set, which we also saw in the introducing example, and also in the absenteeism data set. Of course, there are some additional experiments in the paper, which I will summarize in the following. So we also achieved good performance with the default hyperparameters. So our method does not rely on an extensive hyperparameter optimization, which is also important. Our method is really robust to overfitting, and we have a small effective tree size. So the effective tree size is the size of the tree after pruning. And also, even though our method is not as fast as CARD, we are still efficient for large and high dimensional data sets with an average runtime of only 35 seconds. So if I got you interested, then I've got good news for you, because we have an easy to use pip install ready implementation of this. So if you are interested, then I would really be happy if you maybe give it a try and let me know how it worked out. So it's actually really nice to use and easy. So that's it from my side. Thank you very much for your attention. I would like to point to the QR code on the left for our paper, and I would also be happy if I might see some of you at our poster presentation, which is on Saturday. We got a poster number 328, and also we have some follow-up work which we presented at AAAI, which just extends the method that we proposed here to a weighted tree ensemble, which achieves state-of-the-art results as a performance interpretability trade-off. And outperforms a method like XGBoost and CatBoost on several data sets. So if you're interested in this, you can go to the QR code on the right. So again, thank you very much. And now I'm open to any kind of questions.